to you. Currently, I'm a first-year PhD student in Lilly SCSE-NTU, and my research interests mainly focus on knowledge transfer in NLP. And first of all, let me introduce the background of the pre-trained language models. In several years, many research focus on the word representations that use a dense vector to represent a word. This method can convert the discrete signals to the continuous signals. Furthermore, it can also represent more features with limited dimensions. For example, we can use a two-dimensional space to represent so many words in this figure. Can you see the slides now?
I can see the slide. Pascal, maybe you can log out and re-enter the Zoom.
Well, okay.
Yeah, because the rest of us can see the slides.
Okay.
Thank you.
Thank you. So I'm continuing. And then with the word representations, many works also focus on pre-trained word representations that learn some word embeddings from a large labeled corpus. And this provides a good initialization point. And it also contains some semantic information. For example, the vector king minus the vector man plus the vector woman is similar to the vector queen. So this representation may contain some semantic informations. And based on that, some other words focus on the pre-trained language models. The pre-trained word representations only pre-trained parameters from embedding matrix, but the pre-trained language models also pre-trained parameter for the contextual encoder. This can learn some universal language representations and obtain a good initialization. More importantly, it also has a regularization method to provide some more robust representations. So based on the PLM, we have many downstream applications. But first of all, we need to know how to use these representations. One of the most simple method is fine-tuning. And in my previous work, we noticed that the pre-trained language model was pre-trained from some general source domain, but our downstream task is in the target task. How to transfer knowledge from the source domain to the target task? In this figure, we propose 3 general ways for fine-tuning. The first one, the black lines, it is directly fine-tuned with the single task. And the second one, the blue one, is first we apply a further pre-training, and then we fine-tune the checkpoints for obtained by the further pre-training on the downstream single tasks. And the last one is the red lines that in addition to further pre-training, it also applies multi-task fine-tuning to better utilize the knowledge from the pre-trained language models and the other tasks. And first of all, the single task fine-tuning. Simply, we add a classifier layer that is also known as the task-specific model to the bottom of the PLM. Then we jointly optimize all the parameters for the PLM as well as the task-specific model. As the most widely known PLM, that is BERT, it has 12 layers, and we experiment and on each layer, and we notice that on task classification task, the last layer can usually achieve the best accurate rate, and the first layers will usually obtain a worse accurate rate. So we also apply the further pre-training. That firstly, we apply pre-training tasks on another label corpus U, then fine-tune the new checkpoints on the downstream tasks. And label corpus U, we have three kinds of unlabeled corpus. The first one we call the within task pre-training. That we further pre-train the corpus from the training set of the target tasks. For example, the target task is IMDb data set, and we use the unlabeled corpus to apply the pre-training task. And the second one is in-domain pre-training. For example, the IMDb data set is a movie review data set that aims to predict the sentiments of the reviewers. So we also have another different data sets, review data sets, and that is in the same domain. So we use we use the corpus from the same domain to further pre-train. That is called in-domain pre-training. Lastly, we also have corpus from many other different domains and contains the further pre-training corpus, and it is called cross-domain pre-training. In summary, our further pre-training stage can be summarized as follows. That is, first from the source domain, that is the pre-trained language model, for example, the BERT, and then we use the further pre-train to transfer the knowledge from source domain to the target domain, and then we use fine-tuning to transfer the knowledge from target domain to the target task. And firstly, we explore the further pre-training steps. We noticed that if in the IMDb data set, we only pre-train 100,000 steps can obtain very good checkpoints that for the downstream fine-tuning. And this, we believe that it is because within about 100,000 steps, the pre-trained language models can obtain enough knowledge for downstream tasks. It has already transferred from the source domain to the target domain. So it do not require much more training steps. After that, we also have experiments in the in-domain and cross-domain further trainings. And we select three domains like sentiment, question, and topic. In this table, the last column without pre-train means without further pre-train. We notice that every downstream task can obtain a boost performance with the further pre-trains. Some obtain the best performance in the within task pre-train, and some obtain the best when it is in domain pre-train, and some obtain the best in the cross domain pre-train. So all these results shows that further pre-training is very useful to transfer knowledge from the source domain to the target tasks. Also, we have a comparison with the models before the PLM, and in this 8 data sets, we noticed that the BERT fine-tuning with the in this ITPT fine-tuning means in task further pre-train, in domain further pre-train, and cross domain further pre-train, and so this can obtain the best performance. And it is significantly better than the results obtained before the PLM. Then we also explore about the learning rate. We noticed that a lower learning rate is necessary to make the PLM overcome the catastrophic forgetting problems. This can also this result is also be confirmed in the next experiments that that we use layer-specific learning rate to, and in this experiment, each layer has its layer-specific learning rate, and the last layers has a small no, last layer has a large learning rate, and the first layer has the small learning rate. And in this experiment, you notice that the learning rate kept in about 2.0 e minus 5. It is the most suitable learning rate for the BERT fine tuning, and it is also this result also shows that in the PLM fine tuning, we must keep the learning rate in a very low level. Or with the aggressive learning rate, it may have the categorical forgetting problems that the knowledge from the pre-trained language model may be loose. So in addition to this, we also have some other problems. First, we know that fine tuning usually achieves better results than the feature extractions. But the fine tuning strategy itself is simple, but has not been fully explored. So how can we maximize the utilization of PLM without introducing external data or knowledge? That we only use the downstream tasks and the downstream data set, and as well as the PLM to obtain the best performance. To solve this problem, we try to optimize the training objectives. Here's the model architecture of this work. First of all, as the input X and the label Y, we have the current model BERT, and as well as the teacher BERT. The teacher BERT is self-assembled from several checkpoints that sample from the experience pool. After that, we compute the output losses by the current BERT as well as the teacher BERT. Then we have two loss. The first loss is the task-specific objective. That is the same as the objective in the original fine tuning. And then another loss is a self-distillation loss. Then we weighted these two laws to optimize the parameter from the current model. Then we save our checkpoints to the experience pool for the next iterations. So with the training, we can obtain with the help of the teacher model, we can obtain a better student model. And with a better student model, we can obtain a better teacher model in future. So these interactions may make the training process more stable. And first is the first one in this model architecture, there are two main points. The first one is a self-ensemble, and the second one is self-distillation. And the self-ensemble is firstly sample some checkpoints from the experience pool. Then it uses parameter averaging or logistic voting to compute the output of the teacher models. In summary, it has two kinds of average. The first one is the parameter average, and the second one, it can be regarded as the result average. So with this self-ensemble, we can obtain the logics by the teacher models, and then we use self-distillation to distill the knowledge from the teacher model to the student model. As there are two kinds of self-ensemble, we also have two kinds of self-distillation. The first one is the self-distillation averaged, and this first to compute the average of the parameter average of the teacher model, and then use the MSE as the distillation loss. And the second one is self-distillation voltage that it first averaged the output of the teacher model and then use the MSE loss. With this loss, we can obtain again on many downstream tasks. And as this table shows that our methods can obtain a better score on every downstream task on the blue benchmark. And this, we also apply our fine-tuning strategies to the 24-layer model that, for example, the BERT large, robot large, and so on. We also noticed that our fine-tuning strategies is useful in both the 12-layer PLM and the 24-layer PLM, and it also be useful in BERT and robot and other PLMs. So our fine-tuning strategy is general and can be used in most scenarios. And here are the convergence curves. And as shown in this curve, we notice that the baseline model of the BERT space in the blue lines, that it did not, it cannot obtain further improvement in the last two epochs, but our methods can continuously obtain the improvement on the last epochs. And here's the main gain of our fine-tuning strategies. Also, the loss curve also shows that with some small data set, for example, the MRPC as well as the RTE, and the self-distillation loss is large and the task specific loss is small. So here we need to small factor of the self-distillation loss. But in some large data sets, for example, the QNLI and the MDB, and we do not use such small self-distillation loss. And our self-distillation and self-ensemble can also be regarded as a regularization term to change more robust PLM for the downstream tasks. And in this table, we also have a comparison with some other baselines. For example, the BERT bay means the fine-tuning, the BERT fine-tuning on the downstream tasks, and the BERT volt and the BERT average means that we changed some different, we changed several models with the different random seeds and use the result ensemble as well as the parameter ensemble to try to obtain again. But we noticed that our self-distillation can obtain better performance than the simple ensemble. And we also compare our methods with the other baselines that introduce some external knowledge or data. For example, the MTDNN, it is a multi-task deep neural network that applies the multi-task learning on the PLMs. And these, but our models are single task, are based on a single task, but we also obtain comparable or even better results comparing with the MTDNN that use the external data. So in this way, we do not apply some external data or knowledge, but we can obtain a comparable or even better performance than the methods with some external data. So this shows the effective of our proposed method. Also, we mentioned some simple tasks to apply the PLM. However, there are some other challenging tasks that PLM cannot perform well. For example, in the key phrase generation, that aims to predict a sequence of key phrases with a given input document X. And in this task, the transformer even performs worse than RNNs. So we claim that in this task, there are much uninformative contents, and the transformer, self-attention will have interactions globally. So the information is dealt in the global text. So we need to sparse the attention. Firstly, we have the trunking that separate the input document manually that force the model to attend less range. Then we sparse the matrix of attention marks that we have the attention marks with 3 parts. The first one is the lead. That means that every token will only attend to the lead K tokens. And the second one is neighborhood mask. That means that every token will only attend to its K neighborhoods. And the last one is the top K that mask. That means that every token only attends to the top K tokens with the highest attention scores. And in this way, we can sparse the attention to reduce some uninformative informations, to reduce some unuseful informations. Also, we also apply the relative multi-head attention to introduce the direction informations. With this improvement, we can obtain comparable or even better performance than the RNN models. In this table, we notice that the method with the TF means transformer, it performs significantly worse than the model with the RNN. But with our methods, we optimize the module structure and sparse the attention marks, and we can obtain a better performance. Also, the ablation study shows that when the beta is 0, that means that we do not apply the neighborhood attention, the performance drops most. So we can conclude that the neighborhood is the most important part in this task. So to aim to these challenging tasks, we noticed that the vanilla transformer architecture is not suitable and the PLM does not work well. So the optimization of the module architecture can obtain the better results. After that, we also have some optimization on the evaluation matrix. It is the same as the key phrase generation tasks. The traditional evaluation score is the F1 score that only considers the exact match predictions. For example, when the ground truth is the natural language processing, and there are 2 predictions. The first one is language understanding, and the next one is the apple tree. Both of the scores are 0, but it is obvious that these 2 predictions is not the same, or it is not in the same level. For example, that language understanding is partially correct, but the apple tree is absolutely incorrect. However, key phrases are very short. As you notice that the natural language processing, it only has 3 tokens. Therefore, it is not suitable for some n-gram-based matrix. So is there any fine-grained matrix for smooth evaluation? In this work, we proposed a fine-grained score that contained in 4 perspectives. The first one is a token level F1 score that compute the F1 score in the token level instead of the phrase level. The second one is the token level edit distance. We use the dynamic programming to compute the edit distance in token level and then renorm the distance by the target length. And these 2 score in the token level can measure how similar the prediction and the ground truth. The next two score is in instant level. The first one is the repetition rate penalty. And this penalty is designed that prevent from generating similar key phrases. And it will penalize when the predicted words appears more times than that in the ground truth. And the last one is the generation quantity penalty that prevents generating key phrase only with high confidence. It encourages the model to predict more key phrases. And it will penalize when the number of the predicted key phrases is not equal to the number of the ground truths. And with these four kinds of fine-grained score, we combined it and designed a two-stage reinforcement learning framework. The black line is the original reinforcement learning framework that used the F1 score as the reward. Then the blue line is our two-stage reinforcement framework that first used the fine-grained score as the reward for reinforcement learning, then use the F1 score. And we also use BERT, the pre-trained language model, to compute the word similarity between the traditions as well as the ground truths. And this score we called FB score. And we also applied the FB score as the first stage reinforcement learning and the F1 score as the second stage reinforcement learning. With our two-stage reinforcement learning, we obtained state-of-the-art results on the main data sets of the key phrase generations. And in this experiments, we noticed that the only one stage reinforcement learning with the FG score, that is, it cannot significantly improve the F1 score, because that in this stage, the model are encouraged to generate some partially correct key phrases, but it is not. But it cannot obtain a higher score than the absolutely incorrect phrases. So we apply the second stage of reinforcement learning with the award of the F1 score to optimize the key phrases from partially correct to the absolutely correct. So those two-stage reinforcement learning can be regarded as first generate some particularly correct phrases, and then optimize the partially correct phrases to the absolutely correct phrases, and to improve the F1 scores. So here I conclude some optimizations on different perspectives. And in the future, I noticed that the prompt may be one of the methods to transfer knowledge from the pre-trained language models. And prompt is an engineering that aims to create a prompting function. And with this function, it can help the PLM to predict the answer. For example, in the test classification task, the input X, I love this movie, and then it has a template, for example, the X, and then it has another word, the movie is blah, blah, blah. And the model, the PLM can predict the Z, and the answer Z can also map into some labels, for example, the gray, fantasy, and so on. That is a positive, negative, yes or no, and so on. And in the, for example, in the test generation type and the summarization task, and as the input document X, and we also add a template too long, don't read, and a Z, and the PLM can predict the Z as the summary result. So it has some advantage that the first one is it can better explore the potential of the PLM, and that it avoid the gap between the pre-training and the fine-tuning. As we know that the pre-training task is to learn a language model, but the fine-tuning task is use some task-specific fine-tuning. For example, the classification, you use a cross entropy, and for the summarization, it use the other optimization. So there is a gap between the pre-training and the fine-tuning, but the prompt can avoid this gap. Moreover, it also effective in many source-limited scenarios such as few shot settings. And for example, come back to the examples. When you tell PLM that I love this movie and the movie is Z, and the PLM, because it learns a lot from the large scale unlabeled cover, so the PLM is more likely to predict some positive results in the in this given input. So in many source limited scenarios, prompt can be very effective. The last and the most importantly, prompt can make all the tasks consistent in the same approaches. For example, in previously the understanding task is to predict the labels, but the generalization task is to generate the tokens. It is not the same, but in prompt it is the same. That it reformulate the understanding task, for example, the classification task as the generation task. It reformulate the classifier to generate a new token. So it makes all the tasks consistent in the same approaches, and it means that in the future maybe we can have the universal method to adapt almost every downstream task. However, there are also some challenges. The first one is that prompts require carefully tuning in some specific domain, and the interoperability of prompt is limited, since that in this example, the prompt, the template is manually designed, and we can know that this may be helpful to the downstream task, but in many other cases, for example, when the template is not a hard token, but it is a soft embedding matrix, embedding vectors. So in this case, the prompt is not readable, and the human beings cannot understand the meaning of the prompts. So in this case, the interpretability of the prompt is limited. However, fine-tuning usually has better performance in large-scale supervised scenarios because fine-tuning has obvious objective, but the prompt it only fine-tunes the some kinds of parameters, and it is more likely to like unsupervised or self-supervised tasks. So fine-tuning usually has better performance in large-scale scenarios. The last challenge is that the transferability of prompts cannot be fully explored. For example, if you export a prompt from a task, and it cannot be easily transferred to another task, so the transferability have not been explored. And here are the advantages as well as the challenges in the future of the knowledge transfer in the NLP. And this is all. And for my talk, and today I firstly introduce some knowledge transfer methods to transfer knowledge from the PLM to the downstream tasks. And I also introduced some future directions to the knowledge transfer. So that's all, and here's the Q&A sessions. Is there any problems here?
Hello, Yige.
Hello. Yeah.
Okay. So I see you mentioned that the learning rate can reduce the catastrophic forgetting problem, right?
Yes.
So why it can reduce the forgetting problem?
Yeah, and we can see in this figure that with an aggressive learning rate, firstly, the loss cannot be convergence. And more institutionally, we can explain that with aggressive learning rate, the change of the parameter will be more significant than small learning rate. So it means that with the large learning rate, the parameter will change to some change much significantly. So it may lose some information that's stored or in the original PLM. So to have the categorical forgetting problem.
So is there any theoretical proof for this experimental result, or just based on the experiments?
We do not have theoretically proven. We only have some empirical results.
Okay, thank you.
Yeah.
And I have another question. What is the difference between the in-domain training and the cross-domain training?
In-domain training and it is have many. It is not very different. The in-domain pre-training means that we pre-train in the same domain. For example, in this table, the IMDb, the Yelp data set, all these three data sets are the sentiment data sets, but the Check and the Yahoo answered it is a question data set, and it is not in the same domain. So we can know that in the sentiment domain, the croppers are for sentiment predictions.
So domain means the task. Different task means different domain, right?
Yeah.
Is there any experiment to transfer a data set to another data set?
Yes, here are the results. This one and this column is that we use Yelp. This line, for example, the IMDb line, IMDb row, means that we use IMDb dataset as the further pre-training corpus, and fine-tuning on the IMDb dataset, fine-tuning on the Yelp F, fine-tuning on Check, Yahoo, and so on. And the all sentiment means that we combine the all IMDb, Yelp F, Yelp P dataset as the pre-training corpus, and then fine-tuning on the downstream datasets.
Okay, so it's a little different from the computer vision. I think cross data set can also be called cross domain training. Do you think so?
Yeah.
Okay. Thank you. Okay, that's my problem.
Thank you. Does anybody else has any more questions? You can just unmute yourself and ask, or you can type it into the chat and I will read it out. Okay, if we don't have any more questions, then thank you, Yige. Thank you very much for talking to us about your work.
Okay.
Okay, and I think this is the end of this SLS talk.
Okay.
Bye.
Okay, thank you very much.